Math 1314, Tyler Junior College, Section 3.5, Rational Functions. So, here's where we've been so far in Chapter 3. We started by looking at quadratic functions because their graphs were very predictable. Parabola opens up, parabola opens down. Then we transitioned to a general polynomial function where there was no cap on how large the degree could be. And so we discussed things like in behavior, we discussed things like y-intercepts and x-intercepts, multiplicities and behavior of x-intercepts. We ran into a problem where finding x-intercepts required solving a larger polynomial equation equal to 0. So we built a technique for factoring larger polynomials using division, but we had to come up with a divisor, which led to the rational zero theorem and a bunch of other things. At this point, we're pretty much done discussing polynomial functions and their graphs. So we're going to transition to rational functions. Now, what do I mean by rational functions? Keep in mind that rational from a mathematical perspective means a ratio. So it makes sense that a rational function is a function of the form f of x equals p of x over q of x, a ratio of two other functions, but specifically two other polynomial functions. So in essence, we're taking two of the types of functions we've previously seen, putting them on top of each other, and now we're going to study that category of functions. Before we get into the nitty-gritty about their graphs, let's talk about domains of rational functions, which is a discussion we've actually already had back in Chapter 2 when we were discussing combinations of functions. So this is almost more of a review than an introduction to a new concept. That said, I am going to introduce you to a little bit new terminology and symbols, if you will. Specifically, the domain of f of x equals p of x over q of x is, we'll call it capital D, and we'll define the domain in set builder notation. Here comes the new symbols. This symbol that kind of looks like an E or kind of looks like a Greek letter epsilon is a symbol that means is an element of. It states the relationship between a single value and a set of values. For example, I am an element of all professors at Tyler Junior College. Me being a single entity, and the set of professors being a collection of entities. This double script R is the standard symbol for all real numbers. Now we had another way of representing all real numbers before in interval notation from negative infinity to infinity. But in higher level math classes, it is very common to refer to the set of all real numbers with the double script R, and to state the relationship between a single element and a collection of values using the element symbol. So, I'll leave that up there. So, what is our domain? Well, it's the set of all real numbers, all x's that are elements of the real number, such that, well, what's the one thing we have to avoid in a fraction? We have to avoid the denominator equaling to 0. So we want all the real numbers that make the denominator, which in this is represented with q of x, make the denominator not equal to 0. So let's find them. Let's find the domains. Let's start with f of x equals x minus 5 over x minus 3. If we just use the template set up by the definition, we would say that the domain is the set of all x's in the real numbers such that x minus 3 is not equal to 0. And although that's an adequate description of the domain, it would be nicer if we were explicitly stating what numbers we're excluding. In other words, if we solved this inequality for x. So we could say the domain is the set of all x's in the real numbers such that x is not equal to 3. Because 3 is what would make x minus 3 equal to 0. Now, when we saw these domains previously, we were writing them in interval notation, and I don't want to abandon that. I just want to compare it to set builder notation. We could draw a number line, but let's think about it. If we shaded a number line, we would shade in every number except 3. So to describe the number line that was shaded in, we would start at negative infinity, and we would go all the way to 3. But we would have to exclude the 3, because it's explicitly excluded, and so we would need a parentheses instead of a bracket on the 3. That's not the entire domain, because now we need to union that interval with everything on the other side of 3. So it would start at 3, again with the parentheses, and go to infinity. It's actually pretty easy to write interval notation for all numbers except this one. You just stop at the number you don't want, close the interval, union, open it up again, and keep going. Just remember to use parentheses. Let's take a look at g of x. G of x equals x squared minus 9 over x squared minus 7x minus 8. On this one, it may not be as obvious what the values are that make the denominator equal to 0. So maybe we should start by solving x squared minus 7x minus 8 is equal to 0, which will tell us specifically what we don't want. Feel free to get out the quadratic formula, but I set this up so it will factor. It will factor into x minus 8 and x plus 1, the numbers whose sum is negative 7 and whose product is negative 8. Well, if we set each factor equal to 0 and solve, we get x equals 8 and x equals negative 1. But be careful, that's not the domain. That's precisely what I don't want. Therefore, the domain is the set of all x's in the real numbers such that x is not equal to negative 1 or 8. If we were to write it in set builder notation. If we were to write it in interval notation, we would need not 2 intervals but 3, because we would have to make 2 stops at the numbers we don't want. Starting at negative infinity, the first number we would encounter that we need to exclude is negative 1. Union. Continuing after negative 1, the next value we would need to skip is 8. So we need to end that interval at 8. But then we need to pick up everything after 8. So 8 to infinity. Either notation is acceptable for the domain. Just read the instructions on the question you're working, whether it's an online question or a question out of a book to be written in pencil and paper. Let's take a look at h of x. Same thing. We want to avoid the denominator equal to 0. So let's find the numbers that make it equal to 0. Now, some of you may already be seeing through what I'm putting in front of you here. If I solve x squared plus 1 is equal to 0, we've played this game before. We can solve it by using square roots since there's only one x term. So move the 1, square root both sides, don't forget the plus minus, and of course the square root of negative 1 is still defined as I. So what does this mean if we're looking for the numbers to exclude from the domain and they're not real? Well, the definition of the domain starts by saying x has to be a real number, and these aren't real numbers. Since the only solutions to x squared plus 1 equals 0 are not real, and we're only considering real numbers, this domain has no exclusions. This domain has no exclusions. And when I say no exclusions, meaning we start with the real numbers and we throw out the ones we don't want. So what's the domain? Well, if you were to write it in set builder notation, you could just say the set of all x's that are elements of the real numbers. You don't have to put a condition because there are no real numbers to exclude. Or you could just say it's the set of real numbers. It's kind of redundant to say the set of all x's that are real numbers when you could just say the set of real numbers. Or you could say negative infinity, comma infinity. All three of these are equivalent ways of saying all real numbers. So just because you have a rational function, it does not necessarily mean there will be values excluded from the domain.